Hey guys, I hope you're having a great Saturday. This is the review guide for Unit 5 on bonding, which covers ionic and covalent bonds. We're going to be covering the review guide, the whole part. I'm not going to post an answer key until Monday, so please make sure to watch this video. You can pause any part while we're going through it, so that way if you need to write something down, that's a possibility. Also, feel free to remind message me if you have any questions. I do have my phone with me, so yeah, let's get started. I went ahead and had a copy of the review guide as a PDF, and we're going to start going through it and discussing it together. So for the first one, I have my copy too. For the first one, the properties of ionic bonding. So remember that the first paragraph only has to do with ionic bonding. It states with the first question, which bondings are formed by blank? And that's transfer of electrons. And that specifically is valence electrons. Remember from the previous unit that valence electrons are the electrons on the outermost shell of an element. All right. Next sentence states that ionic compounds are composed of a metal and a nonmetal. If you reversed the answers and said nonmetal and a metal, that is totally fine. It's the fact that you have a metal with a nonmetal. Remember that metals are your cation, that they carry a positive ionic charge, and that the nonmetals are going to be your anions, and they carry a negative charge. So the next line states that ionic bonds are so strong because they have a crystalline lactic structure. Again, crystalline lactic structure. Now, we covered this in the very first PowerPoint, and this is covered on class notes number 1. You can refer back to that. Both of those are on eClass. If they are by chance not published in public, let me know, message me, and I'll double check it after we get done with the video as well. Those are there, so that's where the answer came from. Remember, we talked a lot about salt and how hard it is, and this is why. So next, they have a very high melting point. It is high melting and boiling point, and form electrolytes in water. At the very first part of this unit, we talked about electrolytes in water, what they do, especially for athletes, helping them keep their nerves going through games, everything. You have electrolytes in water. Athletes need extra electrolytes, especially because when they sweat, they put out salt, a little bit of the natural body salt, and perspire. So that is why electrolytes in Gatorade, Smart Water are so important. All right, next line. Bonds between a metal and oxygen are called oxide. Anytime you see the word oxide, you automatically know that it's a metal and it has oxygen with it. All right, bonds between metal and a nonmetal. Everything that's a nonmetal, except for oxygen, when they bond, forms a salt. We talked a lot about sodium chloride, how that's table salt, and the formation of that. All right, on the next part, I added some and this is not something you have to add, but I added the names of each of the different formulas down here, formations of the symbols with the anions and the cations. So then, the first one, SBR3. That you do not need to circle. You do not need to do anything to it because it is a covalent bond. SB and BR are both nonmetals and nonmetals. All right, so MgO, that is an oxide because you have magnesium and oxygen coming together and bonding and forming an ionic bond. And that, when you write it out, its name is magnesium oxide. Next one on your list was ClO2. And that is chloride, chlorine, and oxygen. And those are going to be a covalent bond because it makes chloride dioxide, chlorine dioxide. I know it says chloride. I need to change that. All right. Next one, IF5. He is going to be a covalent bond. Again, iodine and fluorine. When you combine them together, they're nonmetal with a nonmetal, and that becomes iodine peptafluoride. And later on in this review, we'll cover covalent bonds and why they have a prefix in front of it. In this case, for 5, it's penta. All right. The next one is Na2O. Sodium is a metal. Oxygen is a nonmetal. So thus, it forms an ionic bond. Because oxygen is involved, this is going to be an oxide. All right, next line, you have NaCl. Sodium is a metal. Chlorine is a nonmetal. When you come and bond together, that's a metal with a nonmetal, again, ionic. Thus, it is a salt because you have a nonmetal who is not oxygen with a metal, and he is sodium chloride. All right, N2O3 is a covalent bond, nitrogen and oxygen. Nitrogen and oxygen both are nonmetal and nonmetal. Thus, it's going to be dinitrogen trioxide. Again, remember that the 2 represents di and the 3 represents tri. You only, again, use prefixes when it is a covalent bonding, not when it's ionic. All right, next one, you have KCl. K represents for potassium. Cl, chlorine. So it forms a salt. Thus, it becomes potassium chloride. All right, CH4. CH4 is a covalent bond because carbon is a nonmetal, hydrogen is a nonmetal. You're going to have carbon tetrahydroxide. Now this is important, that is hydroxide and not hydroxide with an O in the middle. It totally makes a different element. So, ALN. Now that may look like an I, but that is for aluminum, Al, and then N representing nitrogen. They form a salt. Aluminum has a +3 cation charge. He is a metal. And when he forms a relationship with nitrogen, he forms a ionic bond. becomes a salt, and he forms aluminum nitride. So remember that when you write the name, when you write a name, you're writing the first and last name, just like people, first name, last name. And a lot of people need to change their last name when they form a relationship. So when writing a formula, and this is for, again, ionic bonding, when writing an ionic formula, the total positive charge, so that would be your cation, must be even with the total negative charge. Again, that's your anion. Because the number of electrons lost must equal the number of electrons gained. All right, they have to be even. This is why I keep asking you, +2, -2, is it 0? When we're forming these ionic names and these compounds together, they have to equal 0 together. So always write the symbol of the cation or anion first, followed by the symbol of the anion. All right. I should have circled cation right there because that was a question. So always write the symbol of the cation first and then follow it by the anion. So the crisscross method is what we used for a shortcut to be able to form and write when they don't have an even charge. So sometimes a cation and an anion might be paired up. And let's say this cation had a +3 and your anion had a -2. So the crisscross method was used to be able to figure out how much of each element you need to be able to write the correct symbols for the formula of the compound. All right. So write the name of the cation as it appears on the periodic table. So this is important. Remember that we had a few different types of ionic bonds. They're all the same, like ionic formation, but they're not going to be written always exactly the same, like a polyatomic, which you find on the back of your periodic table. Polyatomics, you write as is. When you have a transition metal, remember that transition metals are special. They like to transition. So some of them may have a greater amount of electrons, may not. So example, iron. You can have iron 1, iron 2, iron 3. So thus, if it is a transition metal, look for and make sure you have written the Roman numerals behind the element name. That is key. When you're going from an element name, the whole written out part, potassium chloride, copper chloride, you have to make sure that the Roman numerals are written in the middle. Those Roman numerals represent the charge. So if I had iron 3, so iron is written out, and I'm going to write it on my board. I do have my board today. So if I had iron 3, when I write out his symbol, what that is saying is that it is iron with a +3 ionic charge. All transition metals will be positive. You just have to figure out how many positive ions they have. And that's what the Roman numerals help you do. All right, so to name an anion, which is the last name you're going to be adding, so change the ending. So if it's carbon, oxygen, you're going to change it to an IDE. Remember that in your class notes number 2, there is a list on one of the pages that show you the prefix and how it interacts with the IDE together to help you learn the names. So oxygen, when you write out the name for an ionic compound, will no longer be oxygen. Drop the ending. And you add IDE. He's still oxygen, but what this says is that he has formed an ionic bond, formed a relationship. The IDE stands for being able to form a relationship. You're going to see this in covalent bonding as well when you have a nonmetal. Ugh. All right. Sorry, my cat came over and decided she wanted to get in my lap. And I really don't think a lot of you knew I had a cat. So, fun fact for Monday. So in the example for 2 for naming the anion, the second blank is chloride. From chlorine, you drop the INE and you add the IDE, making it chloride. All right. B states that if any anion is a polyatomic, so the name that you see, that it appears on the back of the periodic table, you do not change. You do not do anything to the polyatomics that are listed on the back of your periodic table. And let me express very strongly, you do not need to know or memorize the polyatomics. You need to know how to write them out when they form a relationship within a ionic formation, but you do not need to memorize them. You will have them on the back of your periodic table during the test. All right, so let's go down here. So all of these on page 2 are ionic formations. It's like weird to be trying to juggle with the camera. So in CaO, at the very top of your paper, page 2, you have calcium, which is Ca, and you have O for oxygen. When you look on a periodic table, you need to remember that this cute little lime green line, also a very thick line on your all's periodic table. Again, you should have a periodic table that has everything labeled and that is your go-to when you use it to study, especially for this test and for the rest of the semester. Remember to keep your favorite periodic table and take notes on it. So, everything, so starting with lithium down, in the alkali metals, the alkaline earth metals, your transition metals, your other metals, and some of your metalloids are going to be your metals, your cations. Then your anions are going to be anything in your purple, including hydrogen, hydrogen's really not going to be in any anions, but definitely in covalent bonding. All right, so the purple, your fuchsia pink, which is your halogens, and then remember that you don't ever use your noble gases, because remember that noble gases are noble. They have a full valence electron. They have already achieved stability due to the octet rule. So they don't like to play with others. So they don't have an ionic charge. So the only non-metals that you are going to be using are going to be these guys, the purple and your fuchsia. All right, back to the study guide. So you should have this marked on your periodic table. All you have to do is look at the periodic table, see that calcium is in the second group. He is a metal. And then oxygen is on the other side of the table in the nonmetals. So you got your cation and your anion. Also, you should have labeled by now, since you had a quiz on it definitely this week, the ionic charges. So look at the top of each of the groups. Group 2 has a positive 2. And oxygen, who is in, let me pull it back up, who is in group 16, has a negative 2 ionic charge. That is all you need to do for this section. Now please, if you have not done this, please do not just copy the answers. Try to practice it for yourself because you're going to have to do it on your own for the test on Tuesday. So, if you have done it and you're watching this to check your work, awesome, bravo. So let's go over it. All right, next one. You have magnesium and you have phosphorus. So that's Mg and P. Magnesium is your cation. Phosphorus is your anion. Magnesium has a positive 2. Phosphorus has a negative 3. We will get to the crisscross method. I will work some of these out down here for you for the crisscross method. So that is why magnesium has to have 3 magnesiums. So each of those magnesiums have a negative 2 charge. So 3 times 2 is 6. So positive 6 charge. Now your phosphorus has a negative 3 charge. So thus, we just need 2 of him to equal that positive 6 charge. So phosphorus has a P2. Because this is ionic, you do not have to do your prefixes. So when I read this out, it's going to be magnesium phosphide. All I had to do was change the ending of phosphorus to an IDE for phosphide. All right, in the next one, here we go. We have an iron and we have an oxygen. So we have Fe and we have oxygen. So oxygen always naturally has a negative 2 charge. So we actually need 2 of the irons to be able to equal 2 of the, to have that negative 2 charge. So it's it's going to be iron, parentheses, 2, close parentheses, oxide. All right, next one. Aluminum, and we have SO4. So when you look at the back of your periodic table, all of you should have this. When you look at the back of your periodic table, you will see that SO4 is a sulfate. He's down right here. SO4 has a sulfate. He has a negative 2 charge. So because he's polyatomic, he's an anion. The SO4 here will have a negative 2 charge. You will need 3 of him in order to equal an aluminum with a plus 3. So you'll need 2 of him. So each of those, after you add extras to it, for aluminum you need 2, have a positive 6 charge. For the sulfate, you will need to have 3 of him. So 3 times a negative 2 will equal the amount of the positive cations. So plus 6 minus 6 is 0. All right, so let's get into naming. I know this can be a challenge for some, so let's look at the first one. We have iron. It tells us iron 2 sulfate. Again, please do not just write down the answers. Practice these. You will have to do this on the test. So I start off with iron 2 sulfate. So what this tells me is that my iron, whoa, boom, iron, because of this guy right here, he's telling me he has a +2. Sulfate, we know as SO4. So I got that sulfate from the back of the periodic table. So he has a -2 charge. So ask yourself, does +2 and -2 cross out? They do. So when they form their formula, it's going to be FeSO4. All right. The next one, copper and nitrate. Copper, this is what you start out with. Ooh, yeah. The question starts off with a copper +2, a nitrate, NO3, with a -1 charge. So the first blank is just asking you to write out what is actually involved. So all you have to do is write out copper, 2, and a nitrate. Those are the two individual elements, well, the polyatomic, the element of copper and the polyatomic that is involved. Then you can use your crisscross method up top to figure out what the actual formula would be. So circle just the numeric numbers, not the charges. Remember when you do the crisscross method, which was mentioned earlier, you do not take the charge. So the 1 is going to be with copper, and the 2 is going to be with NO3. So when I write him out, I have 1 copper, I have NO3, but I don't have just one of them. I'm going to have 2 of them. And this guy is the formula. Okay. This is by the way, I wrote in what type of ionic naming it is. So this is going to be a polyatomic with a transition metal. All right. Magnesium and oxygen. So it starts you off by telling you what elements are involved in this ionic charge. So whenever I have magnesium, I'm always going to start off with Mg +2. And oxygen is O with a -2. So does +2 minus 2 cross each other out and make 0? The answer is yes. So because they do that, the formula is Mg O. So writing this, remember that your cation, you don't change the name at all. You leave it as is. So you have magnesium, and remember, you no longer write out oxygen, but you're going to have an oxide. That you drop the YGEN with oxygen, and you form an oxide, OXIDE. All right. This is very important. You see that magnesium and oxygen are the only two involved. Remember that this is a binary ionic naming. Bi is the English prefix for two. Bi comes from the Greek of di. That's why we use both the bi and di in chemistry. So for the name, binary, it means that you're going to have two elements involved. You're going to need to be able to look at a group of formed ionic bonds, formulas, and tell me which one is binary. Thus, you're going to need to realize that only two elements are involved. All right, next one is copper, and it gives you copper, parentheses 2, close parentheses, fluoride. So working backwards. So you have copper 2, and you have fluoride. You have copper and fluoride. Copper, they tell you what charge it has. So that is going to be Cu plus 2. Then drop the IDE, and that is fluorine, and his symbol is just F. And he has a -1 charge. Remember, I get this charge from looking at the periodic table. Group 1, +1. Group 2, +2. Group 13, +3. Group 14, ±4. Group 15 is a -3. Group 16, -2. And group 17, -1. So, does +2 - 1 equal 0? The answer is no. You can do a crisscross method simply by circling the numeric number of the charge, crisscross them, and now you write out Cu, and because he's 1, I don't need to put a 1, and then F for fluorine, it's going to have 2. This will be the element formula. All right. Again, the copper 2 and fluorine is the ones involved. Next one, you start off with potassium and hydroxide. Out of the polyatomics, hydroxide you're going to be hearing a lot. So just get used to knowing that hydroxide is OH with a negative charge. So potassium hydroxide, I have K, which is a +1, and I have OH, which is a -1. So potassium +1, OH hydroxide, which is a polyatomic, is a -1. When I do they cancel each other out. +1 - 1, does it equal 0? The answer is yes. So all you have to do is write KOH for your formula. Now, potassium is involved, so when you put in what elements or compounds are involved, you just write potassium and hydroxide because you don't change a polyatomic name. All right, calcium and bromine. So it tells you that those are the two that's involved that you're working with. Calcium and bromine. So one, write out the symbols for who's involved. You have Ca, which is as a +2 charge, and then you have Br, who has a -1 charge. So ask yourself, does bromine and calcium and bromine cross each other out? The answer is no. So do your crisscross method. And write out the formula. CaBr2. All right, when you write out his name, you write calcium as is. You don't change him. Remember, that's because he is the cation. So calcium. And bromine, whoa. Bromine is no longer going to have an INE ending, but he's going to be BROMIDE for bromide. All right, again, this is a binary, 2 elements involved. So next one, it tells you that a lithium carbonate. You see that in the naming that ATE is at the end. Because ATE is at the end, you can flip to the back of your periodic table and look for, in the alphabetical order, carbonate. So, lithium has a +1 charge, and carbonate, CO3, has a -2 charge. So, crisscross them. And when you do that, lithium becomes 2, and because there's no increase on carbonate, he stays at C0O3. All right. All right, next one, we're going to speed things up a little. You're going to have copper. You start off with your formula. You have Cu, which is copper, and you have chlorine, which became a chloride. So, just identify that copper and chlorine are involved, and you write that in the first blank. Then be able to identify the charge for copper may be a little more difficult. So go ahead and write out what you do know. That you do know that chlorine has a -1 charge. And you know that there are 2 of him involved. So you're looking for a +2 to cancel the -2 charge that's formed when you have 2 chlorines. So Cu is going to have a +2 because there's 1 of them. Also, you can do a reverse crisscross and know that, hey, I need a +2 over here and I need a 1 over here for a reverse crisscross to be able to identify an unknown charge amount for a transition metal. So when I write him out, he's going to be copper 2 chloride. Again, chloride comes from chlorine. I drop the INE in chlorine to form chloride in the full name. Next one, you have NH4 parentheses NH4 close parentheses 3 with phosphorus on the outside. Remember that polyatomics can be cations and anions. For the most part, a lot of you, we've worked with them just being anions. They can definitely be both, and there are 2 parts of the back of your periodic table that has cation polyatomics and anions polyatomics. So when you look at ammonium, ammonium is a polyatomic that forms NH4, which has a positive 1 charge. Then you see that phosphorus is on, who has a positive 3 charge. All you had to do was for the different charges is to look at the back of the periodic table. You know that ammonium is involved and phosphorus is involved. Ammonium you can find in household cleaning products such as oven cleaner and other things like that. It is highly reactive with bleach. So, ammonium, AMMONIUM, phosphide. Phosphide would be written out, and that would be his name. So, next one, it gives you magnesium, and it gives you a nitrogen. Remember that you change nitrogen to nitride, an IDE at the end. That magnesium has a +2, nitrogen has a -3. So the only two elements involved are going to be magnesium and nitrogen. The next one is Fe parentheses OH close parentheses 3. Coffee, sorry. So, OH is a hydroxide. It has a -1 charge, thus you need 3 of them to equal the fact that Fe, iron, has a +3 charge. The fact that with problems like this, with transition metals that you don't know their charge right off the top of your head, when you look at a formula, FeOH. So when you aren't told automatically what the charge is, and he has 3, do the charge that you know. So OH on the back of your periodic table, hydroxide, has a -1. And there's 3 of him. So meaning he has an overall -3 charge. So iron, there's only 1 of him. So if iron is positive and my OH is negative and there's 3 of them, automatically you need 3, a +3 charge, to cancel out the -3 overall charge. So iron, it's going to be iron 3 hydroxide. All right, the next one, AlPO4, involves a aluminum and a polyatomic. So aluminum has a +3. PO4, which is a phosphate, is going to be a -3. They automatically cross out. They just cancel each other out. So it becomes AlPO4, which is aluminum phosphate. Last one is calcium and sulfur. So just write out calcium +2, sulfur -2. They crisscross each other. They cross each other out. The +2 -2 equals a CaS, leaving you with calcium sulfide for his name. So that has to do with ionic formation. Now, covalent bonding. Covalent bonding is sharing valence electrons. Ionic bonding is the transferring of charges of your electrons. Covalents share. That's why we have the lines and being able to use the Lewis dot structure to form the bonds. So, 2 types of covalent bonds are going to be polar and nonpolar. We talked about how water and oil do not mix. That is because one is polar, the other is nonpolar. Two types of covalent bonds, polar, nonpolar. Polar is unequal charge. So those are unequal sharing of electrons because one atom is more electronegative. Nonpolar is the equal sharing of electrons because the atoms are approximately equal in electronegativity. All right, covalent bonds can have a single, double, or triple bond. The triple bond are the strongest. They're sharing 3 electrons. On the periodic table, in column 17, form single bonds. Column 16 form double bonds. And in column 15 form triple bonds. These information is all from our class notes number 3 if you're looking back. So the question asks, which of the following is the strongest? So you have fluorine and fluorine has a single bond. Oxygen has a double bond between itself. Nitrogen form a triple bond. So it will be N with the 3 lines with the other N. That is a nitrogen. All right, so which is the weakest covalent bonds? So from your notes, single bonds are the weakest. In each pairs, sorry, I gotta change my hip, the way I'm sitting. With each pair, which covalent compound? So you have FeO. Fe is iron. He is going to be in ionic formation with oxygen. He forms iron oxide. So then you have dihydrogen monoxide or magnesium sulfate. Dihydrogen monoxide. One, the fact that it has di and mono, automatically you should think, covalent bond. If magnesium is a metal, he is going to form a bond with sulfate, which is a polyatomic ion. Thus, it is ionic. So diatomic. So really cute way to help you remember diatomics. Diatomics are going to be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So look at your periodic table. Element 7 is nitrogen. Element 7 starts your diatomics. Make a 7 on the periodic table. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So that's 7. 7 diatomics make 7. So there's 6 in this formation. So hydrogen is the only other one. So 7 with 7. Start with nitrogen, element number 7, atomic number 7. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Hydrogen, number 7. It could be a cute, easy way for you to help remember which ones are diatomic on the periodic table. All right, please note that carbon is not in this mix. All right, so which of the following is not a diatomic element? Al is aluminum. He is not a diatomic. What is diatomic? Yes, write the element name. No name using prefixes. Never use mono for the first element. Charge ending with a second electron to IDE. All right, so what in the world does this mean? It means that your prefixes, that in your first element in a covalent bond, such as carbon, if there's only one of them, like carbon dioxide, so it's CO2. Let me write this down for you. So in this one, CO2, carbon is your first element in the covalent bonding. So because there's just one of them, you do not need to write mono, even though mono is a prefix. 2 is with oxygen, so it's going to be dioxide. You will need to know and memorize each of the prefixes for 1 through 10. So mono, 1, di, 2, tri, 3, tetra, 4, penta, 5, hexa, 6, hepta, 7, 8, octa, 9, nona, and then 10, deca. So when you go through and you practice writing the names for your covalent bonds, remember that this has to do with a nonmetal and a nonmetal. So both of them are in the same area. So on the first one, you have carbon and you have chlorine. So you have CCl4. You have C and Cl4. So carbon's in the first spot, and there's only one of him. So you just write carbon. Cl is chlorine. But just like ionic bonds, you change the ending. So no more I-N-E. He becomes CHOL chloride. Now, how many chlorines do I have? I have 4. So because I have 4, tetra goes in front. So I have carbon tetrachloride, CCl4. All right, next one, oxygen. You have O2 together. So you're probably wondering, wait, Ms. D, I'm confused. Why doesn't they have a di in front of oxygen? That is an excellent question. Remember that diatomics, those 7. So that would be nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. In the natural world, we talked about a lot about identical twins that are connected from like the hips down. That's kind of what's going on with your diatomics. They're stuck naturally together. They form a natural bond. So in the real world, O2, oxygen, is O2 in its formation. So you do not have to write anything but oxygen gas for O2. So next one, NH3, nitrogen is first, and then hydrogen. There are 3 hydrogen, so that will be nitrogen trihydroxide. Trihydride. Oh, it's always a tongue twister for me. So, NH3. Tri is going to be represented by the 3. Then changing hydrogen to hydroxide. All right, NO2. You're going to leave hydrogen by itself because there's only one of them. And he's going to become hydrogen dioxide. Last but not least, H2 is a diatomic hydrogen, so it stays as hydrogen gas. So now writing it from a name to a formula. I actually think it's easier to do it that way. So you have phosphorus trihydride. So you are going to have only one phosphorus because there's no mono, there's no di, tri, or tetra, penta, hepta, hexa, any of those in front right here. So 1 phosphorus, P, and then you're going to have 3 hydrogen. Next, trinitrogen hexahydride. So, with his name, Tri is for 3. Nitrogen is written as N. You can get this from the periodic table when you're taking the test. Then you have hepta, so underline him, and then hydride, which is hydrogen. So N3H6. All right, fluorine. Fluorine is diatomic. So because he's diatomic, all you do is write F2. So H2, O2, N2, F2, Br2, I2. All of those, because they're diatomic, you just write them with a 2 at the end. All right, silicon tetrafluoride. So Si at the front, because silicon doesn't have a prefix in front of it, so you assume it's just 1. It is just 1. And then fluoride is fluorine, so he becomes, that should be a 4 right there. I messed up and I realized that. So that is SiF4. That's my mistake right there, guys. So tetra being 4. All right. Ammonium oxide. So ammonium is a polyatomic. Flip over into the back of your periodic table. Identify under your cations that you have NH4, all of them having to do with the nonmetals. So when you add oxygen to that, he becomes ammonium oxide. Now, that's a little tricky to realize that there's a 2 right there. So please remember that with polyatomics, you write them as is. All right. Last but not least, here we go, last page. Comparing ionic, polar covalent, and non-polar covalent. I highly suggest reading over and trying to memorize these. So with ionic, it is the transfer of electrons. Both of my covalent, the polar and non-polar, are going to be sharing. Polar is going to be unequal sharing of electrons, and non-polar, which is like water, is going to be an equal sharing of electrons. All right. With ionic, they have really high melting points. Polar covalent is going to have a low melting point. Also, non-polar is going to have a low melting point. Let's think about this for a second. If I was to take table salt, just pure table salt, and I had a whole thing of just pure table salt into a pot, it would take a very high temperature to melt that pure salt. Where if I put on the stove a thing of water, which one do you think is going to boil first? The salt or the water? So try to keep and remember it that way, that salt is ionic, very high melting point. Water, covalent, it's going to have a low melting point. All right, so ionics form liquids and solids, where polar are going to be also solids and liquids, but non-polar are going to be like liquids and gases. All right, under this part right here is the periodic table review. The periodic table was our unit 4. You guys should be able to fill in this information and to know the different trends. The 3 major trends that I want you to definitely grasp and take away are going to be the atomic radius, which is the distance from the center of the atom to the outermost shell. Remember that we talked about atomic radius that the more electrons you have on the outer shell is just like pulling the stronger magnet in, so they're smaller, even though the valence electrons have more, where when you have a little bit amounts, like group 1, group 2, they're bigger because of the positive protons in the middle and the negative electrons on the outside have that magnetic kind of pull to them. So when there's only one electron on the outside, it doesn't really pull a whole lot of the radius in. But when there's a lot of them, just like groups 16, 17, those both have 6 valence electrons, 7 valence electrons, or our noble gases, who's group 18, who has a full shell, pull very tight because there's more of them. All right, within a period, so when you're looking at the periodic table, when you're moving from left to right, so as I'm moving left to right, it decreases. As you're within a group, when you're going from top to bottom, it's going to get bigger. So, compared to the atomic radii, helium is going to be very small, where still learning to do YouTube stuff. All right, whereas silicon or potassium are going to be bigger because they only have one electron on the outside, and he's 1, 2, 3 rows down. All right, so some practice. It says in each group, identify which elements have the larger atomic radius. Magnesium is larger than ammonium. Magnesium is over here on the periodic table. Aluminum is over here. I think I said ammonium. I meant aluminum, by the way. Then next one, beryllium, right here, Be. And then we have barium, barium, Ba, barium. Down here, same group, but he is 1, 2, 3, 4 rows down. Then we have nitrogen and oxygen. So nitrogen and oxygen. Nitrogen is bigger than oxygen because he has less valence electrons. Then we have silicon, and we have fluorine, which should be over here. So when you compare them on the periodic table, silicon is to the left, fluorine is to the right. So automatically, and also silicon's a few rows down, he is larger. All right, ionization energy and electronegativity. Both of those trends, their patterns on the periodic table, are identical. They're the same. So ionization energy is for the energy it takes to become an ion. How much energy does it take to take in or give up an electron to form that ionic charge? So within the period, moving from left to right in the rows, it increases. And within the group, so up and down the columns, it decreases. In each group, identify which of the highest and ionization energy. So compared to fluorine versus tin, it's going to be fluorine. Versus potassium versus calcium, calcium wins. So in each of the group, identify which is the lowest ionization energy. So lithium versus boron, lithium wins. Magnesium or silicon, that would be magnesium. Then electronegativity, So even though ionization energy and electronegativity have the exact same trend pattern on the periodic table, what is happening in their meaning are different. So the electronegativity is the trend to attract electrons for bonding. So within the period moving from left to right, they increase. Within the columns, going up and down, they decrease. So oxygen versus barium. So oxygen is going to be greater. He is up here. Barium is down over here. So oxygen would have the highest electronegativity. Now, of all electronegativity, all charges to form bonding relationships, fluorine is your greatest. He is number one. He is the rock star of wanting to form relationships and bonds. So ask yourself, why does noble gases not want to form a bond? Think about it. That's because their valence electrons are full. The octet rule is met. They're stable. So they don't like playing with anyone at all. Then phosphorus and chlorine. Phosphorus is right here. Chlorine is Cl, and he is right here. So between the two, chlorine is going to be more electronegativity than phosphorus. He's going to want to form more bonds. But because he's under fluorine, he is still going to be less reactant than fluorine. So chlorine is under fluorine, so thus fluorine is still have a higher electronegativity. All right, I hope this helped. I know it was long, but this was a full review. I am going to make a shorter video to practice ionic formation and covalent bonding. Please let me know if you guys have any questions. Remember that your test is on Tuesday. Hope you guys are having a great Saturday. Bye.